Oh, that's why that's the wrong. God. All right, it's giving me the wrong webcam. Oh, we're just gonna go with it. At the very least, there will be some audio recording. All right. Why do we have to do conversions? If you're in the medical field, do doctors have to do conversions? Yeah, to some extent. They have to use a lot of the same problem-solving techniques that we use in conversions, just a little bit differently. Instead of looking at how many kilograms of ore does it take to get X amount of lead, they might be looking at how many grams of this particular medication do we need to administer to get the concentration in a body up to a certain level. But it's a lot of the same type of things. Like, okay, well, 5 liters of blood, every liter of blood needs to have this concentration, and so on. So it's a lot of the same style of math, even if it's not directly converting miles to meters or something like that. Because, yeah, most of the medical profession does use the metric system because it's easy and makes the most sense. But there will still be times when it's helpful to know how these conversions work, especially when it comes to word problems. Yeah.
Doctors, I chatted with some vets in the summer and we go to farm calls. She would take like 10 minutes, go sit in the truck and pull out 2 of her textbooks and calculator and like.
Yeah, exactly. You're not going to remember it. So the most common textbook that you will go to, that you will want to reference in whatever field you go into, the most common textbook that you're going to need to go back and look at once you start working is going to be your Gen Chem textbook, because it's going to have, every chapter in your Gen Chem textbook is an entire upper division class. You're not going to take all of those, but to get the basics for all of these different subjects, Gen Chem is a really good way of sort of giving you a really broad foundation in a lot of different topics in chemistry. And so it winds up coming back one way or another. And it does, and knowing the basics of how do I set this up as a conversion problem, or how do I get an answer here. It gets repetitive because there's going to be certain calculations for your job that you do all the time. But the first time you do them, it's going to be like, oh man, you're going to get some PTSD flashbacks to Gen Chem probably. And just working with the student workers who are working in the chem labs, prepping labs now, they're going to have to start doing really repetitive calculations that you guys are going to learn in a few weeks. Every week, every time they make a solution, they've got to do the same calculation, depending on what solution is they're making. So there's a lot of places where it will continue to come back, even if you're not directly working in chemistry. And how important are sig figs when you're an engineer? I like this question. Their answer is very important, because you need to know exactly where your uncertainty is. That sounds like a contradiction. You need to know what your uncertainty is if you're going to be an engineer, because tolerances, exactly how much can this bridge carry? It can hold 150 cars plus or minus a car, or is it 150 cars plus or minus 10 cars? That could make a really big difference as an engineer, right? Understanding how uncertainty factors into tolerances and safety parameters winds up being a really big deal. So actually, and that is one of the things that conversions always gets brought up, but there was an issue with the conversion between metric and feet on one of the Mars rovers, and they basically turned it into a very, very expensive projectile because they miscalculated or forgot to convert feet to meters. And so instead of opening the parachute at 100 meters above the surface, it opened it 100 feet above the surface, which was not nearly enough to stop it. So these things do show up, and even rocket scientists screw them up. So it's worth paying attention to. Jordan?
Yeah, same with the Mars climate controller. We actually don't know what happened to that. It either crashed landed on Mars or is currently orbiting the sun.
Right, yeah, it skipped. It was part of the aerobraking maneuver that was supposed to slow it down. And so it either went too shallow and wound up, it's like the 2 options from Apollo 13, for those of you who've seen that movie. It goes too shallow, it doesn't slow down enough, and it just impacts the ground very, very hard. We call that lithobraking. Aerobraking is when you use atmosphere to slow yourself down. Lithobraking is where you use litho, which is rocks, to slow yourself down. So basically smashing into the ground. It's very effective at slowing something down if you don't care about how it ends up at the end. But the other option is that it doesn't slow down enough when it tries to aerobrake, and it winds up getting slingshotted off of Mars and into somewhere around the solar system. But yes, sig figs and uncertainty and conversions still show up as engineers. If all measurements are man-made, so how do we decide which conversions are exact? And how do we know these conversions transfer from system to system? It's a little bit arbitrary, but it's a little bit arbitrary the same way that the first person to decide what a meter was just had to pick a distance. And they said, okay, from here to here, I will call that a meter, and this will be a meter, and everything will be relative to this meter that I just made right here. And that's a meter. That's what a meter is now, because somebody just arbitrarily said, this is a meter. So it is man-made, but you have to have exact definitions somewhere. So they basically just say, okay, well, we know all man-made measurements have uncertainty associated with them when you're measuring, but we can make a definition, say, well, now this is exactly 1 meter by definition. And so that's how you get exact conversions despite every measurement being measured.
Well, you mentioned that they changed the length of an inch to match the metric system.
Yes.
So right there in itself, it's just man-made.
Right. It's very exactly. It's a very man-made system, and it winds up being, in that case, every ruler made after that point was technically a little bit wrong, but it was already really close. It was like 2.54001 centimeters, and then more decimals if you wanted to. It's 1 inch. They just said, well, that's already so close to 2.54. We're just going to call that exact. And then from now on, all of our rulers will be slightly different. Jordan?
I think originally the meter was 1 billionth the distance from North Pole to the equator passing through Paris.
That sounds about right.
And
now it's defined as the distance that light travels in 1/3 times 10 to the 8 seconds.
Yeah. Or I think it might be slightly less. It's like a bunch of random numbers, like 299 million something, something, something.
Right, yeah, so it's more measured numbers there, but they redefined it relative to the speed of light.
Yeah.
How do we calculate uncertainty on color? That's weird because color is qualitative, right?
Yeah.
Is that blue plus or minus a shade? No, so what they do in science is we just take color and we turn it into, color is really just our eyes taking photons and interpreting what the energy of those photons are. Our brain processes that and turns it into the sensation we call light. That's really all your eyes are doing, is they're measuring what's the wavelength of light, what's the energy of light for all of these photons that are hitting your cornea or your retina. So what we do in the science is, if you want to calculate uncertainty, is we turn it into energy numbers instead of color shades. We actually take those colors and say, okay, well, that color is actually this wavelength of light, plus or minus a nanometer. So all of a sudden, by turning it into something that you can measure directly, either in terms of energy or frequency or wavelength, you can describe light in any of those terms. And then there's a conversion. There's a way you can say, okay, well, this region is blue. So it's not that there's uncertainty associated with the colors. It's more that the color is really our brain's way of processing the energy of light anyway. So if we can take that and turn it into numbers, now we can use our regular rules for uncertainty and sig figs. All right, so these are the ones we'll go over on Thursday. They're more random. This one I thought is worth spending time on because we're going to talk about some sort of abstract stuff today. And every third question or so that I get is, why does this matter? Why do we care about sig figs? Why do we care about conversions? Do I really need to know this? Why did anybody spend their time in their life dedicated to this topic that seems really, really removed from reality? I get that. In fact, a lot of times you wind up with people trying to cut budgets by saying, well, let's only do science research on stuff that matters, in quotes. Let's not spend any money on scientific research that has no practical application. And so that's been argued as a way to cut NASA's funding, a way to cut the NSF's funding. and redirect it only towards engineering and medicine projects. But the thing is, you can't always tell when a breakthrough is going to be really, really instrumental in changing the world. So, for instance, the one that I always go to as a good example is James Maxwell. James Maxwell was a Scottish man from the 1800s. And at the time, if the Queen of England had said, I'm going to fund all this research, I want somebody to make a way for me to sit in my palace and talk and have my voice heard in every single household in the kingdom. If they'd just been said, this is the application we want, here's money, go make it happen, they would have never been able to do what Maxwell did. Maxwell was a mathematician, actually, who was being paid a salary that most people thought was extraordinarily large for someone who didn't do anything practical value. But he's the one who actually unified electric force and magnetic force into the electromagnetic force. And he did it basically by saying, well, these two equations are really similar. And if I make some variable substitutions and add a term over here, I can make them one equation. And okay, cool. Now we have one equation. That doesn't necessarily tell you how big a deal that was, but it laid the groundwork for anything that communicates data wirelessly. Starting with radio, TV signals, Wi-Fi, anything that's based around radio signals in general, Maxwell laid the foundation for it with something that nobody thought had any practical value. So, Maxwell was able to fulfill that Queen's request, the hypothetical request, by inventing the radio, more or less. But nobody knew it when he was working on it initially. And the same can be said for almost anything in quantum. If we don't understand what quantum is and how it works, then we don't understand how semiconductors work. And if we don't have semiconductors, we don't have computers, we don't have LEDs, we don't have solar panels, we don't have TVs, we don't have CRTs. We don't have a lot of things that really, really are fundamental for our way of life now. But originally, they're like, what are you talking about, Schrodinger? Cat in a box. That's stupid. Why are we spending money paying you to do research on this stuff that makes no sense? Well, it didn't make sense then. But if you don't pay for the fundamental research that seems like it has no practical value, then you don't get things like computers out of it. And so the free market and engineers are really good at taking science and finding a way to make money and product with it and solving problems with it, but they're not good at coming up with the fundamental science. So you have to fund the fundamental science research in order to give the science to the engineers and companies who can then turn it into a product that they can sell and that changes things. Right, so I know I've spent a lot of time talking about this, but this is a really, really common phrase when it comes to science funding. It's a waste of money because we don't know what it's going to do. It's all a waste of money, right? But it's really, really the book that I read that was really good at explaining this was by Carl Sagan. It was written in the 80s, and he made a lot of digs about Ronald Reagan that could be applied to pretty much every president since. It's very, very timeless, despite the fact he died like 10, 15 years ago. But it's an ongoing debate. Every single time funding comes up, they want to cut science funding. People want to cut science funding because it seems like it's not practical. Here's why we shouldn't. James Maxwell, Niels Bohr, the quantum chemists.
What's the name of the book?
That was from Demon Haunted World. Also, it's a really, really good book. He talks a lot about pseudoscience, which is using scientific terms to sell something that's not real. So, like homeopathic medicine.
Like politics.
Or
We'll stay away from politics mostly.
Or astrology.
Astrology. So astrology is a little bit more further removed, but yeah, pseudoscience, anytime you use scientific words to sell a product that has no effect. So there's a lot of them. You see a lot of them in health and beauty products. Gwyneth Paltrow is awful about it. You've seen the goop, like what was the one she was talking lately about the collagen that's uniquely filtered or something like that. Every time a commercial comes on, I see red for a few minutes.
See that one, that's psychology behind medicine is really
because like almost a lot, even for pharmaceutical, like synthetic pharmaceuticals, like a lot of the work being done is actually from placebo effect. So
Right, there is,
so
and there is,
it's really
yeah, and the placebo effect is a real thing. They can also control for that. That's why we do double-blind studies, right? But there is something to be said for making use of that where it's beneficial.
a lot of the like alternative ones.
Yes, yeah, exactly.
Minimizing placebo effect.
I'm nothing against alternative medicine, but you know what they call alternative medicine that works? Medicine.
Yeah.
Western medicine is really, like, they're really actually good at plundering useful medicine from all over the place. They don't give credit where credit's due, but if there's something to it, they will find it and they will use it.
Yeah, Europe is really good at stealing stuff.
Yes,
a lot
exactly.
A lot of times, like medicine, a lot of traditional medicines, like China has done this too. Like they go into Tibet and they'll find these like traditional medicines that work, and then they'll try to cultivate like from the plants, but the plants aren't really good for cultivation, so they'll end up like bringing that plant species to extinction by overharvesting it.
Right, and then they wind up making a synthetic analog of it that does something similar, maybe better, maybe not. But yeah, anyway, we'll spend a lot of time talking about medicine as we get into more how molecular structures work. General quiz feedback. So make sure you're writing your units on conversions, and this applies to the ICA as well. If I can't tell what numbers came from where, because you didn't write any units on them, it makes it really hard to give partial credit when you don't have the right answer at the end. And if any number that you box at the end as your final answer should have a unit with it, or it should be a ratio or a percentage. But either way, there should be some information that tells me what that number is that is your final answer. All right, so make sure that your units cancel out if you're doing conversions. How do we convert ounces to milliliters? There's actually two different answers for that one, depending on if you're using US ounces or if you're using British ounces. We're not going to get that picky. The ones we're using should have been 473 milliliters to 16 ounces. You did not need to get into fluid ounces versus where I'm not going to make that distinction usually. All right, so, and really once we get past getting used to conversions, we're not going to use ounces at all. All right, so fluid ounces is a volume. Non-fluid ounces or troy ounces is a mass. So since this one was converting ounces to milliliters, you can make the assumption this is talking about volume ounces. And volume ounces and mass ounces are the same if we're talking about water. Right, so if we're talking about water, it's the same. Otherwise, that doesn't make any sense. It depends on what the material is to be able to do this conversion.
So was there an answer? You said it was
473.
And can you show us that real quick?
Yeah. So it was 16.0 ounces, right?
Yeah.
Mm-hmm.
I got 4 sig figs.
Did it start like this, or did
It starts like that.
Okay.
Like you said 473, but I had 4 sig figs.
So that's just a sig fig error. But if you got 473 point something, then you just missed a quarter point per sig figs. 32 ounces is a quart. And then we have a definition that, or not a definition, a measured conversion that says was a 1.0567.
Yeah. To 1 liter.
Quarts is 1 liter. And then 1 liter is 1,000 milliliters. And so if you plugged all this into your calculator, the way I would plug this into my calculator would be 16 divided by 32 divided by 1.0567 times 1,000. Anything on the top you multiply, anything on the bottom you divide by, and you should get 473. If you set this all up properly, but you didn't get the right answer, it's probably a calculator error, meaning you just plugged it in wrong. Right, so double check your work on that one.
It's even 5 sig figs. That's wrong.
So the conversion's 5 sig figs, but we only started with 3 here. And this is a measured number. So if we started with a whole bunch of sig figs over here, if we started with 6 sig figs initially, and we use a conversion that only has 5 sig figs, this conversion is measured. So this would be what controls our sig figs on our answer. Tiana?
I was trying to do it exact, so into like inches cubed and inches cubed to centimeters cubed, and in fact, is that all?
Yes, in fact, you can do it exactly, but the only exact conversion for metric to English is inches to centimeters, right? If you go to gallons, there's a conversion for gallons to cubic inches, and then you can go cubic inches to cubic centimeters. Right, so it actually doesn't even add that many steps, right? Because then the next one would be 4 quarts is 1 gallon. And 1 gallon, 231 inches cubed. And 1 inch is 2.54 centimeters, the whole thing squared, or cubed, I mean. So that's a couple steps, but now we used all exact conversions. So if we happen to have more sig figs at the beginning, we could keep them all. And cubic centimeters is milliliters. So this gets us there as well. Takes a couple extra steps in a cubed one. But this is an even better way, in theory, for getting an exact conversion there. The other thing that I noticed, and you guys are actually better about this than most of my classes are, is usually when I give this quiz, something like half the people who take this quiz mix up megameters and millimeters. The question asked about megameters. If you just type it into Google and say, Google, convert these units for me, Google doesn't know the difference between megameters and millimeters. So Google turns this into millimeters and you get something that's a pretty small number. If you, megameters into feet, I think, right?
Yep.
So if you do that, megameters into millimeters into feet, you get a really small number. If you go megameters into feet, you get something like 10 to the 7. 10 to the 6, thank you.
What was the?
Right, so pay attention to your capitalization here. And actually, I noticed the lab yesterday was taught that as well. On one of the labels on in lab was CO. NO3. Capital C, lowercase o is cobalt. Capital C, capital O is carbon monoxide. So paying attention to capitalization matters a lot when we start looking at compounds too. Because whether it's capitalized or lowercase is conveying information to people. Right, so be paying attention to that. Tiana, did you have a question? Oh, okay. Looked like you had your hand up. No, you're fine now that I know this. Oh, you're sitting here. You're good. Nano years to seconds through some of you. Does nano mean something is smaller or bigger?
Smaller.
Small. So the conversion sheet just says that the multiplier is 10 to the minus 9 for nano, right? It says n nano multiplier 10 to the minus 9. The way to remember how that works is that it's small. Nano is small. So it means it takes a lot of nano years to equal 1 year. 1 year equals 10 to the 9 nano years. Right, and once you go from nano years to regular years, all of our normal conversions still apply. So we can go from years to days, days to hours, hours to seconds. So because a nano year is smaller than a year, it takes a lot of nano years to make 1 year. Or you could write it as 10 to the minus 9 years equals 1 nano year. Mathematically, it's the same thing. My mind would rather deal with a big number of whole objects rather than dealing with a really small decimal, so I prefer to think about it this way. But this is just as correct. It's just like saying 0.01 meters equals 1 centimeter. That's the same thing as saying 100 centimeters equals 1 meter, just reversed.
And in that one, we keep 2 sig figs, right? Even though there's no decimal after the 14.
Correct.
So it should have been like
14.4.
point.
So if it doesn't end in a 0, we're not that picky about it. If it was 10 plus or minus 1, we would want a point there.
Okay.
But if it's a number other than 10 or 0, we can assume that that's a sig fig, and we don't need the decimal there.
What's the answer for that?
0.44
1.4.
or 4.4 times 10 to the minus 1. if you wanted to put it in scientific notation.
I thought it was asking how many nanoseconds in one year.
Right, if you went nanoseconds in a year, then that
That's
was a whole different thing, right?
different.
So I try to be very careful about how I write these questions to, to not be misunderstood. So if it, just part of this one was about remembering that nano can be applied to anything, not just nanoseconds, because that's what we're used to hearing. Nano, you can have nanometers, you can have nano degrees Kelvin. You can have nano whatever you want. It's just that normal number divided by 10 to the 9.
It's 4.4 times 10 to the negative 1 is the answer.
So if you, that's the same thing as seconds. That's the same thing as 0.44, just in scientific notation. You didn't have to put it in scientific notation, but Rose did, so I was confirming this is accurate. So
Asking for 2 sig figs.
these are both equally correct answers.
I would look at the bottom one and say that's sig figs, 'cause it's
Remember,
stupid.
leading zeros don't count. And if you're unsure, put it in scientific notation. Anything you write in the coefficient in scientific notation, you're saying is a sig fig. So if you're unsure, you can always put it in scientific notation. But this is just as correct because that 0 doesn't count as a sig fig.
And we were getting marked down like a quarter of a point, you said? If we didn't put the correct sig fig?
If you just messed up your sig figs, I took off a quarter of a point on each of those 4. So if you messed up your sig figs on all of them, it was 3 out of 4, even if you got the right answer on the whole thing, for each of those 4 problems. So generally what I do is, if it's a bigger problem that's worth more points, it'll be a half point. If it's a really small problem, or 1 out of 4, then I'll do something like a quarter point off for sig figs.
Just because I had to double check this a few times, just because my brain wasn't grasping it. So I went online just to double check, and it gave me 4.4 times 10 to the 8th. Why I'm very confused.
So probably,
Yeah.
so you're off by a factor of 10 to the 9, right?
Because I just Googled 14 nanometers, 2 seconds, and that's what.
So probably what it did is it didn't know what to do with nano, so it just didn't do anything with nano.
Okay.
If you did 14 years to seconds, you would get, that's what you would get, because you're off by 10 to the 9. It's the same decimals, but off by 10 to the 9, which means this didn't get taken into account somewhere.
Okay.
Did I miss the target completely, or did you go through that calculation for me? Because I went nanoseconds.
Okay,
14 nanoseconds to years. I don't know if you're going to count that as missing the target completely, because I was just.
I usually still try to give at least partial credit on a 1 point question. If it's really off, I might just give 0, but usually I'll give at least partial credit. So 14 nanoseconds.
I did.
So you just want to know if you did your way?
I was
right?
just wondering how you're going to grade that. Or are you just going to give it a 0 because it wasn't even close to the target?
If you answer a question that's not the question I asked, then if you answer the question that's not the question I asked, but you do it correctly,
it's the same math.
You might get like a half a point. It's probably
It's the same math because it's the 10 to the 9th.
Right.
Yeah, so it's the same math in essence.
Talk to me after class.
Okay.
So usually what I'll do in a situation like that is I'll make a deal with you.
Okay.
If you wind up with that 1 point being the difference between an A and a B in this class, talk to me during finals week, and we'll make sure that that's not what keeps you from getting an A.
Okay, sounds good.
Probably it's not going to matter.
It's not going to be.
Yeah. One other thing is that you can also submit for any of these file upload questions, or where you have multiple questions that all say file upload. You can just do it once. You don't have to upload a separate file 3 times. Just so you're aware, and in fact that even makes it easier for me to grade too. So don't feel like you need to go through and crop out number 3 when you submit your answer for number 2 or anything like that. All right. We talked a little bit about measured numbers and exact. Just a reminder that a measured number is anything where if you add more decimals, you could make it better. So if I said there's 12 inches in 1 foot, it's not like 12.0 is a better number than 12, right? It doesn't matter. I couldn't make that conversion better by saying 12.00001, right? If that's not inches equals 1 foot, that's not true, right? It's not about 12 inches, it is 12 inches. It's exactly 12 inches.
The zeros go on forever.
Zeros go on forever. So in that case, anytime you have something like that where adding more decimals will never change anything and never make your number any more accurate, then it's an exact conversion. So usually we see those with definitions. The definition of a foot is 12 inches. The definition of a meter is 100 centimeters. Anything that's a measured number is going to be things like speeds. Speed is a conversion that's a measured number. What is sig big is going to come into play, right? If I say that my average speed from here to Sacramento is 62 miles per hour, is it exactly 62? No, right? If I had a better speedometer, or if I measured my numbers more carefully, I could.
Satellite GPS.
Right, if I use my satellite GPS at 62.017. Well, that's a more accurate number. And I could keep going, right? Any measured number means that one, you measured it, somebody measured it. But two, it means that if you had more decimal places, you could make it more accurate.
You just limited to your measuring device?
You're limited to your measuring device, exactly. So densities, distances, speeds, anything like that, anything that's given to you in a problem usually as a conversion, like the density of lead is 11.34. It's not exactly 11.34 grams per milliliter. If we had better measuring devices, we could get more decimals on that. So that tells you it's a measured number, not an exact number. All right, and so for the most part, your conversions that are going between the same unit types, like length to length, are mostly going to be exact. When you start doing things like using a speed to convert from a length to a time, those are going to be measured conversions usually. And if you're going between systems from imperial units to metric units or vice versa, those are usually going to be measured with one exception, which is 2.54. And that's the only exact conversion for imperial to metric. All right, so we are now 40 minutes into class, which is okay. I really don't mind taking time to go over the quiz so you guys know how you did and how things are going. So for the 10 to 15 minutes before break, does anybody have any questions on ICA? Grace?
Spheres, iron or copper and lead spheres.
Ah, I like that one. But I like that one because it actually puts like this is a case where I can give you very, very little information and you can still get a real answer once you figure out how to do it. Did you have any specific questions?
Yeah, how to do it.
How to do it? Okay.
We'll start. Pretty short and sweet.
What do we know?
Total mass, total volume.
Don't know. Oh my God.
What else do we know?
Density of lead, 11.34 grams per centimeter cubed.
And copper.
This actually made so much sense when you explained it.
Well, let's see if I can do it again.
So frustrating.
All right. So first off, all we did is write down the things that are in the problem statement, right? First off, looking at the things I wrote down, you might notice that our densities are in grams per cubic centimeter, our volumes are in cubic centimeter, but our mass is in kilograms. So as long as it's an easy conversion, we might as well take this in kilograms and make it grams, because then everything matches up, right? All our masses are in grams, all of our volumes are going to be in cubic centimeters. So if we just multiply by 1,000, we get grams. And that's just sort of housekeeping, because that's just going to make sure that we're not going to wind up with any weird conversions in the middle of our problem. Now, all of the masses we know will be in grams, and all of the volumes will be cubic centimeters. Now, Grace, what else do we know about the total mass? What is the total mass?
The weight of both of them.
The weight of both of them. So how could we write that, Grace? Hold on, your thought, Jordan.
So the mass of the copper plus the mass of the lead.
Nice. We just wrote an algebraic expression. Doesn't necessarily look like it's all that helpful. It seems like it's so simple as to be worthless, but it's true. We know that this is accurate, right? The total mass is these two masses put together, and that equals a number. So we could do the same thing here, couldn't we? And what would that look like? I'll open it back up to the floor now.
427 equals the volume of copper as well as the volume.
Yeah, we do the same exact thing except with volumes instead of masses. We know that that's true as well, right? Our total volume is equal to these two pieces put together.
Yes.
And if we had more pieces, we could just add more terms on here, right? That's going to make things trickier down the road, and I'll explain why in a minute. But if we had more pieces, we can always just write this. It's a little bit like saying if you have two percentages that make up the total, they have to add up to 100, right? All we're saying is if this is our total, these are our pieces, this has to be an accurate equation. What is density?
Mass over volume.
Mass over volume. So if we're talking about density of lead, what is it? Mass of lead over volume of lead.
Yeah.
Which means we could do the same thing here, right?
I was dead silent. Sorry. Sorry. It made me very uncomfortable.
This is a very quiet classroom. I kind of like it for that. It's not so echoey, but it does make it really quiet. So how does this help us? I'm going to clear this a little bit.
We can maybe put things in terms of other things and then plug and chug.
So this is called a system of equations. We have 4 equations now that use the same variables.
Yes.
And as soon as we have the same variables, so anytime you have a system of equations, however many variables you have, that's how many equations you're going to need to get an answer. So if we have 4 different variables, mass of copper, mass of lead, volume of copper, volume of lead, and then our 2 down here reuse those same 4 variables, we have 4 equations and 4 unknowns, we can solve that and get a number, or we can get a number answer for all of those. Right, so that's having 4 distinct algebraic expressions. This was actually the hardest part of the problem. You don't have me to show you. These are really easy to write once I have you asking pointed questions and leading the witness, so to speak. But at the same time, getting here is probably the trickiest part. From here, all we're going to do is we're just going to start substituting.
It's not so clear from what they said.
It is. You just need to know that you can look at it this way.
Yeah.
Anytime you have a mixture of things, you don't know anything about the composition of that mixture other than it has 2 components, you should start thinking about it like this. Like, okay, well, what can I write that I know is true? So the way we actually start solving this, so once you get to this point, once you get 4 equations, 4 unknowns, you know, you're gonna want to keep these boxed on part of your paper and leave them where they are, because this is where we're starting everything else. All we're going to do from now is just a bunch of algebra to try and simplify and get to a number. So once you get these 4 equations, you keep them boxed separate from everything else so you don't rewrite them accidentally and screw something up. This is the one time I will tell you it's okay to write numbers without units. Because all of our mass units match up and all of our volume units match up. And it's going to make the algebra look way easier if we remove the units. I'm allowing you, with system of equations, you're allowed to not write the units when we're doing your algebra. Okay? At this point, if you have Wolfram Alpha, you can actually just plug this into Wolfram Alpha. If you have solver on your calculator, you can just plug this in and say solve for x. You need to redefine, mass of copper to be x or something like that, and use x's and y's instead of subscripts. But solver works at this point. But if we're doing it by hand, all we're going to do is start solving these equations for one or more of these variables and plug it into the other equations. So you could do that at the top by saying, okay, if I took equation 2 and said, okay, well, 427 minus the volume of copper equals the volume of lead. Well, that doesn't look like it was that helpful, except I can take this and I can plug it in for volume of lead right there. I don't like dealing with addition and subtraction any more than I have to when I do substitution, so I wouldn't start with equation 2. I would start with equation 3 and 4. Because then we can say things like, okay, if I take equation 3 and I multiply both sides by the volume of lead, you get 11.34 times the volume of lead equals the mass of lead. So same equation, just rearranged, right? I can do the same thing for equation 4, couldn't I? 8.90 volume of copper equals mass of copper. Right. Once I have these rearranged and I solve for one of these variables, all I'm going to do is I'm going to take this and I'm going to plug it in for mass of lead in equation 1. And I'm going to take this and plug it in for mass of copper in equation 1. And I can take 3 equations, equations 1, 3, and 4, and turn them into one equation that has fewer variables than I started with.
So it's the mass of lead 1 over 11.34. Or the volume of that first one, would I just divide each side by 11.34 then?
Not yet. So I see what you're talking about for equation 2 now, right?
No, just that top.
Just for this one?
Yes.
So once you solve for the mass, this, whatever's on the other side of the equal sign, can be plugged in anywhere mass shows up. Mass of lead shows up over there. So you can say 11.34 times the volume of lead plus, I'm going to do the same thing for, we'll do it one step at a time, plus the mass of copper equals 4.36 times 10 to the 3rd grams, but I'm going to leave off grams. All I did was I took this expression and I plugged it in where the mass of lead was. So that is most basic, that's what they call substitution in algebra, right? Took 2 things that are equal to each other and I swapped them. And I can do the same thing for copper now, right?
But then you still have 2 variables in that.
We still have 2 variables.
So you're at the same amount of variables. But not for the 3 equations. I see.
Yes. So we still have 2 variables here, but overall we basically got rid of mass. Mass doesn't show up in either of these 2 equations anymore, right? And now we can use equation 2 and we can do this one more time. Because we can say, okay, well, equation 2 is 427 minus the volume of lead equals volume of copper.
I just don't understand.
So, understand these first 4?
I understand how they're set up, but you don't have volume and you don't have mass, so how are you moving them around to figure it out?
You have
So-
volume, that variable on the right side over here. He's just making one of the volumes equal to this number subtracted by the other number, right? You're just putting one in terms of the other, and then plugging it in, and then just checking.
I don't know why you'd be moving it around if you're trying to get information that you don't have, and you can't get it.
Watch. So right now, this equation might be true, but it still has two variables, and we can't get a number out of it, right? If we do this one more substitution, if we plug this in for volume of copper, so 11.34 times volume of lead plus 8.90 times 427 minus the volume of lead equals 4.36 times 10 to the 3. That still doesn't look friendly, but now it's just a bunch of numbers with only one variable. We're able to basically combine all four of those equations into one mega equation. And now it's just algebra. Now it's just one equation or one variable in there. So now if we could do some distribution in combining like terms, we can actually get a number for the volume of lead. Nothing. Okay.
So you see how on the bottom it's got BPP and VC, right? Okay. So you see how that equation right there in the middle of the screen equals VC, right? So all he took because VC has to equal 4.7 because we need that VCU is that plug. So all he's doing is taking those equations. Just give one. So instead of
Good news, I'm not stupid, I'm ignorant.
You haven't seen this trick yet. That's what it is. Once you know how to do substitute, all this substitution is, there's more complicated ways to do substitution in a math class to make this take fewer steps or make the algebra easier. But this is the one that works no matter what. If you have four equations, four unknowns, take an equation, solve for one of the variables, and plug it into one of the other equations. Take the next equation, solve for one of the variables, plug it into one of the other equations. As long as you can't reuse the same equation, or you're going to wind up solving for something that's obviously true, like volume of copper equals volume of copper.
Yeah.
But as long as you make sure you're not reusing the same equations more than once, all you have to do, solve for one of these variables, plug it into something else. So all I did was I used equation 1 basically as my master equation. I solved this for the mass of lead, plugged it in there. Solved this for mass of copper, plugged it in. Solved this for the volume of copper, plugged it in. And now I get something. It's a pain to simplify, but I get something I can solve. And again, this is, at any point in this, you can go to Wolfram Alpha and say, type in the equation and solve it. So for instance, I'll clear off the board so you can see here in a second. There are lots of solvers built into calculators. There's lots of other options. I like Wolfram Alpha because it's powerful and it's free. But there are lots of other things you could use. But once I get to, especially once I get to where there's only one variable, if I don't want to do this by hand to get a number, I can just say, I can just replace volume of lead with X. And I can type in here and 11.34 times X plus 8.9 parentheses, I might as well flip the multiplication, times 427 minus X equals 4.36 e to the 3. Solve for X. And in theory, it goes, when I do that. Oh, there it is. Okay. 11.34 plus 8.9 times 427 minus X equals, I did not interpret that well. So times 10 to the X. We used to do that. So if you see it put a lowercase e in, that's using e the constant, which is a 2.17. You don't want to do that. But it gives you an answer. It gives you an exact answer. That's 27,985 over 122. If you hit approximate form, you get 229.39 for the volume of lead.
Wait, hold on, what was that?
So your answer, I typed in, this is what I typed in.
Cool.
And then this is one of the things I like about Wolfram Alpha is it says this, when you type something in, it then says, this is what I thought you said, to make sure that you didn't type something you didn't mean to. Like I used E as an abbreviation, then it didn't like that. Or it took it, but it didn't mean what I thought it meant. So then I can look at this and say, well, this looks just like the equation I started with, right? And then here's the result. X is approximately equal to 229.39. Okay, so it's a bunch of algebra if you're trying to do this by hand. A lot of places to screw up, but if you make sure that you that your answer is reasonable, then you usually will catch things like missing a negative sign. Because if you miss a negative sign, you might get something like your volume is negative. If you get a negative volume, you know that that can't be true. You don't even need to go to this far. You can actually start from a system of equations and type it all directly into Wolfram Alpha. I know it's about time for a break, but give me 1 second to show you this.
And now with BPB, we don't, I just put that into anywhere else to solve everything else.
So we say X is mass of copper, Y is mass of lead, M is volume of copper, and N is volume of lead. Just for the sake of, because Wolfram does not understand subscripts. So for the sake of typing this in, I'm just redefining those as regular math variables. But I can actually just go up here, type in all four of my original equations. 4360 equals X plus Y. And then in between equations, you just hit a comma. I'm just doing that instead of times 10 to the 3 because it's easier to type. 427 equals M plus N. 8.90. I did that backwards. 11.34 equals Y over N. 8.9 equals X over M. So just these equations typed with variables and with no units. And we wanted to find the mass of copper was what the original question asked, right?
The mass percentage.
Mass percentage. So we could just say solve for X. Might take it a second now. It spits back your four equations that look right to me. Make sure you didn't mix up your X's and Y's. Then it gives you an answer for X and Y and N and M. And so you don't have to do all this by hand. You might notice that the decimals are a little bit different on N because of the way it rounds when it solves them. But yeah, so you don't have to wade through pages and pages of algebra. But I don't think I would necessarily plug this into Wolfram when I was still right here. I might do some of the substitution by hand until I got to only one variable, because then it's easy to type in, and I don't have to worry about all the combining like terms and all that. But you can, as soon as you get here on your homework and on take-home test, it is a valid math step to say, I used Wolfram Alpha. You still have to get these right or your answer is going to be wrong. You still have to know how to type it in. But it's a valid math step. It's considered showing your work in this class to say, I used a solver. Here's what I got for my answer. Or you can do all the math, the algebra yourself, and you'll get the same answer at the end.
What is the actual answer since it's asking for a percentage?
So mass percentage. So we wound up solving for volume of lead originally, right?
Right.
That brings me to one more thing I want to talk about. Volume of lead was 229.
Sure.
cubic centimeters. The question asked for the mass percentage copper. So I didn't worry about what variables I was canceling out and what variables I was keeping when I was doing my substitution, because as soon as I get one of these answers, I come back to my original 4 equations that I have boxed at the top of my paper, and I can plug it into any of these and find out the rest of them. So if I want to know if I have the volume of lead and I want mass of copper, I can start by getting a volume of copper. Because if I plug in 229 right here, I can get volume of copper, right? And once I have volume of copper, I go down here and I plug in volume of copper here, and I can get mass of copper. And mass of copper that we solved for here was 1760. We're only keeping 3 sig figs. So if we want the mass percentage copper, percentage is always the part divided by the total, right?
Times 100.
Times 100, thank you. Here's our total mass. Here's our part. So our mass percentage for copper is just going to be 1.76 10 to the 3 over 4.36 10 to the 3 grams and grams times 100. Mass percentage copper equals
30%. Masking. That's what I
40.4%.
there we go.
So Sean, real quick though, when you do this, like algebra on your paper or whatever, because or even just with like your own calculator, not online, the first thing, because I did the same steps you did, but my volume wasn't 2.29. It had to go up to 2.30 because of sig figs and whatnot. But because of that, it changed the rest of the equations. So how off should it be though for the percentage?
So the reason that we have sig fig rules is so because if you follow all your sig fig rules, then you shouldn't be off by more than about 0.2. So if you get 40.6 or 40.2, depending on where you round it in the middle, that's all considered the same. 40.5,
40.1.
40.1, sure. Close enough.
Okay.
Because if you happen to get unlucky with the way you're rounding, if you rounded a bunch of numbers that were really close to 0.5 and you rounded all of them down, it was like 0.48, 0.47, do that a bunch of times in a row, then you can wind up with it making you off by a significant amount. In theory, eventually that should average out because you'll wind up rounding up by just as much if you do it enough. Right. But if you get unlucky with where you stop to round a bunch of times in a row, you could get off by more than just plus or minus 1 in this last place.
Okay, cool.
But it should still be 40 point something for sure. All right.
So M up there, that was the volume of copper.
M was the volume of copper, yes.
Right, cool.
Mark?
Did you do the next problem?
Let's take a break first.
Break, yeah.
Okay, yeah.
Yeah.
And actually, this one's not due till Thursday at midnight, so we might, so that we can still cover some new material,
Okay.
we might save that one and go over it on,
Yeah.
okay,
On Thursday.
on Thursday. But I can at least get you started on that at after class, okay?
Okay.
Yeah.